Does that sound new?
I don't think so.
I like it. Okay, now guys, we're ready to talk about the homework. No, I do not want the Loom helper. Are you still recording? Okay. All right. So guys, this is important. If you don't understand what we're about to talk about is important, allow me from a distance to share with you this. I'm about to hand this to you. And guys, this is a summary of everything that you learned last time and a summary of what you're going to learn today. But guys, the way that this works, just showing you, this is strong acid-base titration. That's this. Guys, the bottom of this is weak acid-base titration, which is what we're about to do. So guys, everything that we're going to talk about today, which amazingly is the last really hard day in this class ever.
I'm actually going to be sick.
Guys, all of this comes in the context of this. Guys, the calculation that we're going to do to end the day today is probably the most intricate and tricky thing you'll do in this class. But guys, you are going to understand it through the lens of what you've already learned. So therefore, this is important. So, guys, let's talk about what this thing represents. So the idea is this. First of all, these may have caught you a little bit off guard, but guys, these are the calculations that we did in both the virtual and the simple titration lab. Remember, we had vinegar, we added sodium hydroxide, we titrated the thing, and then guys, we found out some things about it's all just dimensional analysis. You okay here? Okay. This then, guys, after these, is where this gets a little more exciting. Because now what we're doing is we are looking at the pH of solutions as we are titrating them. But guys, remember, these are strong titrations, which means the thing that's going in is strong and the thing that's sitting in the little spinny flask is strong. And as a result, this is not equilibrium molarity math. This is subtractive quantitative math. Did any of you pick up on this, like the first two rows in an iRace box? Guys, this is subtractive math that gets us to how much, so the subtraction, right? How much of the unreacted ion is still there. And then, guys, we convert to a molarity and then to pH. Yeah?
Should that be HCl because the rest of it is HBr?
Where?
At the end where you have the concentration.
No, so... Sorry, I can't even pull this off with a straight face. I was going to say something really stupid. Never mind. Yes. Again, as I mentioned a second ago, guys, totally did this whole thing copy and paste, right? My bad. I was going to say something.
You're going to want to do the one on
Molar her. Because apparently I can't type HBr. No, not her. Did I do it down here too? All right. Yeah, thank you. I was going to say something about a nuclear process that turned chlorine into bromine. Yeah, see? So, guys, again, the big idea here is the quantitative subtractive math that gets us to the point where we understand what's left over, and that determines pH. You okay with that? Okay, then, guys, a couple other interesting things we need to talk about. Guys, what about this? And I don't even know if there's a question like this in the homework, but let's talk about it. So, guys, you'll notice the molarities are the same, yes? Good?
Wait.
Molarities, can I touch my board? Yeah. So, guys, the molarities of these solutions are the same. Good? What if the volumes were the same? pH 7, and that's the point. So, guys, if your molarities are the same and the volumes are the same, then these would be the same, and that subtracts to none left, and that's pH 7. Is that okay? Now, guys, what about this? So this is our standard, right? This is our unknown. But guys, let's say we are at pH 7. So if we were at pH 7, but if this molarity was 0.4 molar, twice the molarity, what would this volume need to be in order to balance that out? Half of it, right? Guys, and what do we call that condition where the amount of acid and the amount of base are the same? Equivalence point. Yes? What is equal? And guys, at the equivalence point, the number of moles are equal, and because this is quantitative, there's no unreacted ion left and the pH is 7. So guys, that's the equivalence point. Is that okay? Equal moles. But then guys, thinking about indicators, the equivalence point isn't necessarily where the indicator changes color. What do we call the place where the indicator changes color? The end point. So guys, that's the term you need to know. It's the end point, and we call it that, and this will help you remember. It's called the end point because that's where you end the titration. Woo! What do we need to talk about? You're all good? Oh, please, yeah.
So, I guess my question is, we were, like, with all these calculations, we were finding the, so like with the molarity and stuff, that's the molarity, so like the HBr in the first one or whatever.
Yeah.
That's the molarity of the stuff that's, or like, that's the moles in the solution.
Can I ask you a follow-up question without distracting you?
Yeah.
The moles of what in the solution?
Moles of HBr.
Right. But
Yeah.
more generally, it's the moles of stuff that hasn't been reacted. So if, for example, here, this is our standard, right?
Yeah.
So here's our acid, here's our base, this is our standard. So when there's less of this, by moles, when there's less of this, then it's the concentration of the unreacted acid. I don't know if this is going to be there. I hope it is. Yes. So now here we've got more of the standard added. So now it's the molarity of the additional base that we put in.
Okay.
Is that okay?
I think so.
So the idea is that I've never done this before, but let's see if it works. So down inside the flask, right, with the spinny thing, you've got a fixed amount of the acid. And as you're adding the acid, or the base, if you're adding less base than there is acid, so there's more of this and less of the base, then you're going to have unreacted acid, and that'll determine the pH. When you've added the same amount, then they balance each other out, equivalence, and then it's 7, right?
Assuming their molarities are the same.
Their moles are the same.
Their moles.
Their moles are the same. But if their molarities are the same, their volumes would also be the same. So again, you've got a fixed amount of acid. As you're adding base, if you haven't added as much base as acid by moles, then the pH is going to be determined by the unreacted the acid. Then when you've added the same amount of both, we're at equivalence. That's pH 7. But then if you keep dumping in base, we will have reacted up this much acid, and then there's going to be extra base, and then that determines the pH.
Yeah.
Is that okay?
Makes sense. So then the two-dimensional analysis questions are just determining how many moles of each we have.
Bingo. Yep. And then you always subtract big from small. So it doesn't really, you can see that the way that I set this up, this number should be backwards. It should be negative. But when you do these subtractions, what you really want to do is subtract big minus little. And the big minus little gives you the amount of stuff, whether in this case it's base or whether in this case it's acid. Big minus little gives you the amount of stuff that's not reacted. And as a result, that's what determines the pH. And then we just have to divide by the sum of these converted to liters, and that gives us the molarity. Is that okay? You asked a really good question. Spencer, are you stretching, or are you thinking, or are you questioning? Perfect. Guys, what else on this homework? Bueno? Bueno. Hi. So, guys, let me record, and I will pause. Allow me to record this. Say again. That's right. Parting is such sweet sorrow. All right. Boom. I'm going to hand you those papers that I showed you from a distance. But guys, I want to start here. So, guys, let's be clear on what we're doing. We're now going to talk about weak titrations. But guys, when we do, and maybe drawing this would be helpful, we got to be really clear about what's weak. And I don't know that you need to draw this, but I'll take the time just to drive home the point. There we go. All right, so guys, it goes like this. You know my mad artistic skills, but you get the idea. So, guys, up until now, what we did last time is this was strong, the stuff in the flask, and that was strong, the stuff we were dumping into it. So, guys, now, moving forward, one of these guys is going to be weak. Is it the one in the burette or the one in the flask? In the flask. Guys, this is going to become our weak component. The stuff in the burette will always be strong. And guys, understand that does not matter if this is titrating a buffer, titrating a strong acid, or titrating a weak acid, whatever it may be. Guys, what is in that in the burette is always strong. So you're always adding strong to something. Understand, it doesn't have to be the acid. Guys, this could be a weak base. And then this is going to be something like hydrochloric acid. But guys, at the end of the day, the stuff that's getting added is always strong. If it's not, that's ugly. That's right. Those are your competing equilibria, and have fun with that. Okay, so guys, with that said, let's go back and let's build. Guys, let's build on some solid ground. And it goes like this. So guys, here we have the titration curve that we looked at last time. And you may remember, and if you didn't, this is the way we talked about this when we looked at the homework. Guys, we think of this as having 4 regions. We have the initial pH, we have the pH before equivalence, we have the pH at equivalence, and then after equivalence. So guys, couple minutes, it's a bigger question. Just sort of grab the person next to you and talk through that. What is the logic, not doing the math, but what is the logic and the mathematical process that allows you to figure out the pH in each of these regions? You don't need to write anything down, but talk about it. How do you find the pH in each of those regions? I love that Sharp went right to the easy answer and said, at equivalence, it's 7.
That's my specialty.
There you go.
If they ask me on the AP test, tell us the pH of one point in this graph. I'll tell them it's just the pH is 4. The pH is negative. Oops. I still think the pH should be a scale where it starts at 0. And it goes up and down from there.
It would seem our pH is actually 26.
So, guys, sorry, I probably distracted you. So, your ability to be successful today is going to be built upon the correctness of the answers you come up with now. Do you need another minute, or can we talk? Are we okay? Anyone need a little more time? Okay. So, guys, let's talk about it. You don't need to write this down because it's in the thing I'm about to give you. But, guys, the idea is this. How do we find the pH before we've added any of the standard? It's just pH is equal to the negative log of the concentration of whatever this is, right? So in order to find the pH, if this is 0.1 molar HCl, plug in 0.1. If this is 0.1 molar sodium hydroxide, plug in 0.1. Of course, if you do that, then you get a POH, and you got to do it from there. But guys, are we comfortable with that? Okay. All right. Yep. Sharp's right. That one's 7. But now, guys, this. How do we find the pH before equivalence? And guys, this was the deep dive that Nora got us into. So how do we find the deep dive, or how do we find the pH before equivalence? Sorry, I shouldn't have grabbed a lifesaver. Okay, so how do we find the pH before equivalence? What do we need to know? Well, guys, we need to know the number of moles of base. In this case, let's just call it base, of the standard. We need to know moles of standard. We need to know moles of the stuff in the flask, right? Then what do we do with those two numbers? We subtract them. Keep going. Sorry. We find the difference, we subtract. And then what do we do with that difference in moles? Divide by the volume, the adjusted volume, find molarity, and then take the negative log, right? Okay. So then, guys, what about up here? How do we find this pH? It's exactly the same thing. Okay. So, guys, with that said, right?
It's the same process.
It's the same yes, thank you. When I said thing, I don't mean it yet. But guys, the idea is it's the same process, only then you'll have an excess of the titrant and not the thing being titrated. Did I give you 4?
Yeah.
All right, guys, so do this. Reading over this chart that I gave you, and let me throw this up on the screen. I believe I have a picture of it. Yep, right here. Okay, so guys, throwing this up on the screen, this is where we are. So notice that we've got our 4 regions. We've got initial, we've got before, at, and after equivalence. And then, guys, over here, we've got strong acid base. So this is the way I represented it. This is equal to the concentration of the original solution. And then, guys, just pH is equal to the negative log, right? Well, first of all, this. Guys, what do you notice about these? They're the same because we established that the process is the same. But, guys, read the way I wrote it and then jot notes, make corrections. Because if your description was different than my description, guys, feel free to write in those spaces, write around them, and make my words more like your own words as you would describe that subtraction process, moles, and then subtraction, and then converting to molarity.
The volume change, when it says remember volume changes, that's talking about the adjusted volume.
Yeah, so if you've got 50 milliliters of the acid and 49 milliliters of the base, that'd be 99 milliliters. So guys, again, maybe you wouldn't have used the same words that I do. So make this useful to you. Or maybe don't do anything with it at all, because you're like, it's in my brain, I don't need it in words. Totally up to you. You guys okay? Sitting good on this? Okay. So, guys, now what we're going to do is we're going to start looking at weak titrations. So, in order to do that, so guys, here's our strong titration. Allow yourself to sort of drink this in a little bit. So again, our titrant is the strong base sodium hydroxide. Our how about this? Our acid is a strong acid, but it's also a 0.1 molar strong acid. How do I know this is 0.1 molar acid? Alright? Yeah. So, guys, with that said, what I'm going to do now is I'm going to superimpose a weak titration curve over the top of this. The base will be the same. The molarity will be the same. But now we're going to superimpose a weak base titration over the top of this. So guys, I have a question for you before we get, oh, sorry, I'm drawing dots. Guys, I have a question for you. So what I'm about to do, actually, let me do it here. So guys, now I'm going to superimpose a weak titration over the top of this. I have a question for you that you should be able to answer. So let's say this is 0.1 molar HCl. And I'm going to make it 0.1 molar vinegar because that's what we do. Guys, relative to this, when I superimpose, and guys, I want you to talk about this. When I superimpose the titration curve of 0.1 molar vinegar over the top of this, where will the line start relative to 1? Will it be at 1, above 1, or below 1, given that the molarities are the same? They're both 0.1 molar solutions, the HCl or the vinegar. So guys, where will the line start relative to 1? At, above, or below? Talk about it. You buy it?
So, and that's the oh, no, sorry.
All right, guys, I love the way you're talking. I love the way you're thinking. And you were right. It looks like this.
It's fancy. Swoopy.
So, guys, yeah, swoopy, right? So, guys, let's be clear. This is our original, the blue, right, is our original strong acid titration. Now, the green is our weak acid titration. Again, talking with somebody near you, similarities and differences. Besides being swoopy, when we're going to talk about swoopy in a minute, it's interesting. Guys, what do you notice comparing the two? What are things that catch your eye? Talk about it.
Well, is different. Well, it's has the same like flaws, but it's different. It just stays the whole
Oh, yeah, no, it's way higher. It's not as heavy.
Probably have to have it. Why did it still reach?
Standards is because the weak acid base.
It's because it's like a buff.
It's like that's how we're replacing.
And so,
hydrochloric acid.
So yeah. And that's going to make more acetate, more conjugate base, and that's how the second one is more.
No, that's what I'm saying. Okay.
All right, guys, let's talk. So let's go back to the question that I asked you previously. And all of you, I think, landed on this idea. Guys, let me grab writing utensils really quickly. So one of the things, and again, we talked about this in sort of the intro. Guys, notice where this starts. It does not, the molarities are the same, but it doesn't start at 1. Why not? It's a weak acid. And guys, weak acids do not fully protonate. So we'll talk more about how to deal with that in a minute. But guys, observation number 1 is the pH, and again, equal molarities, right? But the pH starts higher because it's a weak acid. It doesn't fully dissociate, so we would expect it to be less acidic, higher pH.
And the Ka would be different too.
Well, but an interesting point. Remember that strong acids don't have Kas. If we do product divided by reactant, there is no reactant. All of the HCl breaks apart, so the concentration of the acid is 0. So the Ka for a strong acid is undefined. The word that they use in the books is very large. But yeah, so, okay. So guys, other observations. And I want to just turn it to you. Guys, please, read.
The endpoints are like the same because like
But let me challenge you on that a little bit. I agree with you that the endpoints are the same, but let's come back to what endpoint means. It means the place where the indicator changes color, right? So follow along. If we are doing a strong titration, we go do 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 do, and then that one drop goes woohoo, and the methyl red would have changed colors, the phenolphthalein would have changed colors. Off we go, right? But what if we were doing this titration? Do you see that right here is where the methyl red would change color, right? So if we were using methyl red for this titration, it would change color right there, and we would have really messed up data because we're missing all of this volume of the base, right? So question then, would methyl red work for this titration?
No.
But now do you understand why we always use phenolphthalein? Right? Because guys, phenolphthalein's endpoint is above 7. And because it's above 7, it not only catches strong titrations, it also catches weak titrations. That's why we use phenolphthalein, yeah?
Would we use methyl red if we were titrating base?
Yeah, you absolutely could. But again, phenolphthalein is sort of our universal bullet because it does most of them. Although, did you remember in the lab that we did, the virtual titration lab, the last titration we did, it needed a different indicator?
Yes.
It was like, I don't even remember the name of it. But
Isn't that crazy?
yeah, anyway, so sometimes we need different, but for our purposes, phenolphthalein works. Okay, so guys, I'm never going to be able to back out of all of that. So let me just clean it up. All right, so guys, other observations. And Regan, that was great. Go ahead.
The slope of the before equivalence point and the after equivalence
Yeah.
point, equivalence points are different for the weak base.
Interesting,
or
right?
For weak base.
Yeah. And guys, if I may, and John, I know you said this sort of, but swoopy, right? So guys, let's look at that idea. So here, these are about the same slope, right? But coming out, it's more flat. But guys, did you notice this little bit right here? The swoopy bit? Guys, we're not going to talk about this now. I'm going to say it, and then John, I'm going to be really impressed if you figured this out. So guys, here's the deal. Initially, when we dump the strong base into the weak acid, the pH jumps. It goes, woohoo! And it jumps really quick, but then it starts to increase more gradually. Guys, what's happening is this acetic acid is buffering itself. Is that what you were thinking? That scares me.
Kind of thing.
Guys, the fact that you can, and please, if you don't see that, you're human. Like, seriously, right? Guys, we're going to talk about this next week because we're going to go do both of these titrations with an actual pH meter plugged into a computer. And guys, you're going to generate these graphs. We're going to talk about concave up. We're going to talk about concave down. We're going to talk about points of inflection. We're going to talk about maximum slope. Those are all first and second derivatives.
So
we'll talk more.
calculus.
Yeah, but we're going to let the computer do it for us. Yeah, but guys, what's actually going on here is initially we don't have a lot of acetate ions sitting around. But as we do this, the acetic acid gets converted into sodium or into acetate, and then it buffers itself, and the pH doesn't rise as quickly. We'll talk more later. Guys, what else do you notice? Please.
I think it's interesting that they both have the same. Oh no, they have the equivalence point happens at the same volume.
Good. Stop right there. So guys, the equivalence point happens at the same volume. Why?
That's what I can't figure out.
Yeah, so guys, let me write this down. We are saying, for example, that this is 0.1 molar HCl, and this is 0.1 molar CH3COOH. But guys, their volumes are the same. We need to include that. Their volumes are the same. So guys, think about this. Even picture the math. If their volumes are the same, and if their molarities are the same, what about the number of moles of these as we have compared to number of moles of those? They're the same. Can you picture the dimensional analysis? Start with the volume, convert to moles, and then that gives you, with the molarity, right? Start with the volume, moles to liters, well, liters to moles, and then you know the number of moles. And guys, they're the same. It doesn't matter if it's a strong acid or a weak acid. If you have the same volume of the same molarity acids, whether it's weak or strong, you've got the same number of moles of those particles. That's why the equivalence point is at the same volume, because this sodium hydroxide has beaten the crap out of this acid. And it doesn't care if it's beaten up on HCl or if it's beaten up on vinegar. Guys, it's just beating up on the acid. And so it would take the same amount of base to react up with the acid regardless of which one it is. Yeah.
So at the end of this titration, we aren't going to have any unprotonated acid.
Mm-hmm.
Because it's all going to get pulled out.
Exactly.
It's going to be, it's
like
like
a
the
random
equilibrium is going to
buffet.
shift all the way.
Right, and that's why these are superimposed.
So interesting.
Yeah, so after equilibrium, after equivalence, you ain't got no acid left. It doesn't matter if that's a strong acid or a weak acid. After equivalence, there's none left. And this is just like dumping base into water. And it's exactly the same all throughout. Okay? Guys, you ready for the really crazy bit? Oh, can I do one? No, you do one.
I was gonna say, does that mean that the slope of that point evens out?
Tell me about that point.
Sorry, the after equivalence?
If you push up, right here you got a laser.
So, here,
Yep,
you're saying that after this point it's like dumping base in the water or whatever?
correct.
So wouldn't that mean that the pH is gonna level out and be even?
Well,
You're
so,
still adding
but
base.
then you're talking about creating the Satan juice, right? Because in theory you can keep, in theory you can keep just adding more and more base, right?
Yeah.
And you're just, oh, the Satan juice thing is wrong because the molarity is the same. So would it level out? Yes. Because eventually what's going to happen is, like, say for example, the sodium hydroxide is 0.1 molar sodium hydroxide, right? So as you're adding that sodium hydroxide into what is effectively water, you're diluting it, right? Because there's water there and you're adding the base. But eventually you could add so much base that the little bit of water that was there is just insignificant. So this would in fact hit a maximum actually at pH 13. Because 0.1 molar sodium hydroxide has a pH of 13, so eventually it would level out there.
That line isn't actually linear. It's
Well, no, it is linear, but eventually you're going to get to
I
the
feel like-
pH of the base.
Would it curve though to stop, or would it just go and then flat?
Yeah, I mean,
I feel
in
like it-
theory it would be asymptotic because it's always diluted a little,
Yeah.
but at some point it becomes insignificant. You guys okay? Now can I share with you the really ugly, scary thing? This. Guys, the pH at equivalence is not 7. Let's talk about why.
Because it is not.
Just want to be.
Guys, why is the pH at equivalence not 7? You don't need to write any of this down. But guys, what we need to do is we need to talk about the chemistry that's going on inside of here. So let's do this. So we've got a weak acid. And we've got a strong base. Is that the correct arrow? Is that equilibrium or is it quantitative? Let me ask differently. Why is that the correct arrow?
Because the sodium
It's not-
hydroxide
Because this is strong. Guys, this is none of that messing around namby-pamby equilibrium crap. This is a strong base kicking butt on this weak acid. So what are our products? Sodium acetate and water. Now,
Wouldn't it be CH3C? Yeah.
oh, thank you. That's important. Thank you.
We somehow kept.
Yeah, that's right. So, guys, here's the point. Sodium acetate is a salt. And when we put salt in water, sometimes it changes the pH. And so we go back here and we go, this is like for the test, right? So we go back here and we go, remember our test, we go, sodium is the child of the strong base, sodium hydroxide. So what's McKenna's word? Trash. Now guys, the acetate ion is the child of the weak acid, acetic acid. So this is not trash. So guys, that does chemistry. I have no idea where to write this down. I'll just do it here. And I'm just going to write across this. So guys, this is the chemistry. Acetate ion reacts with the water. And when it does, what does the acetate ion do to the water? Does it take an H or an OH? It takes an H. And so we end up with this. And we end up with hydroxide. And guys, the hydroxide makes this basic, and therefore the equivalence point is above 7. You get to solve that.
All of us, if the salt precipitates, do we have to worry about that?
It won't.
It won't?
No, it won't. Yeah, good question, but it won't.
Oh,
Go ahead, James, go ahead.
So you're saying this is the logical thought behind it, but we're going to figure out how to do it mathematically?
But it's just an icebox.
It's just an icebox.
Yeah, it's just an icebox. Go ahead.
I'm pretty sure this is correct, but I'm assuming that we can like make a rule that says if you're adding a weak acid, no, if you're adding a base to an acid, then your equivalence point is going to be higher than 7.
Correct.
If you're going the other way. Then
Correct, exactly. Yes, that's right. Yep.
Nice.
I was just gonna say the same thing. Like if you have a strong acid to a weak base, is it gonna move the pH down?
It'll be down. Do you want to look at why?
Sure.
Do you want to do it quick? Yeah, so imagine this. So imagine that our base was something like NH3, and then imagine that our acid was HCl. So when we look at our products, we've got NH4 plus and chloride minus, right? So chloride is the child of the strong acid. This is negligible. We're going to use negligible, right? But this is the child of the weak base. So NH4 plus ammonium does chemistry with water. What does it do? Well, it gives a hydrogen to water, and that forms NH3 and then H3O.
Yeah.
And that H3O is acidic and the pH goes down. Yep. Yeah. Is that okay? So guys, what we've got to do now is take all this brilliant logic and turn it into math. So we're going to do these one at a time. And as we do, we are then going to do and then refer. So we're going to solve each one of these 4 initial, before, at, and after equivalents. But guys, after each one that we do, we're going to turn to that chart and go put it in your own, or adopt my words if you want, but we're going to summarize. So guys, it goes like this. So much going on up here. Boom. All right, here we go. So, okay, let's put this in context just to be sure. So now, guys, what we're going to do is we're going to chase the green curve, right? Let's remind ourselves of observations. First of all, the pH doesn't start where it might based upon the molarity because it's weak. Then, guys, this looks interestingly familiar. Then this is not at 7, and then this is the same. Ready to go? Here we go.
Oh no.
Oh, yes.
that middle section is about.
All right, here we go, guys. Put this in context. So we've got 50 milliliters of acetic acid. And it's, okay, so I like pictures. I don't care if you do. I like pictures. By the way, guys, on the AP test and even on tests, you know how we talk about the first thing you do is the most important thing you do? Draw pictures. I do that all the time. Like when I'm tutoring kids, college kids in chemistry, it blows their, I'm like, draw a picture. And you draw the picture and they go, oh, now I get it. So guys, here's what we got. We've got 50 milliliters of 0.1 molar vinegar down in a bucket. How do we find the pH of that? Just an ice box. Forgive me if this is unsatisfying, but I'm going to do this at warp speed. This is kind of fun.
Some people are going to take notes.
God. Whew. Got winded. So guys, the molarity is 0.00134. pH is equal to the negative log of x is equal to the negative log of 0.00134. Did any of you happen to remember the molar or the pH? Oh, I thought it was going to be 4.7. Never mind. 2.87. That's a mess. Actually, that's what a lot of your guys' work looks like. Some of it looks a lot worse.
Mine usually doesn't add units or like half of other things, and it's also hard to read.
And still gets
I told you about this, right, guys? When the last time I went to an AP conference, and one of the guys from the University of Northern Colorado was there. He's one of the guys that writes the questions for the test. Did I tell you about this? And you know, as chemistry teachers, we're sort of in the presence of what's probably like a deity, perhaps a demigod, because he writes the test, and we're like, "Hello, O learned one, what can we tell our students to help them do better on the test?" Have I told you? What can we do? What can we tell our students in order to help them do better on the test? We were looking for some just mathematical conceptual nugget to rain down from on high. His answer was, tell them to write legibly. Because guys, if we can't read it, we don't grade it. So guys, are we good on this? You sitting okay? Sharp, did you feel a little bit of conviction there?
Just a little bit.
That's good. Unfortunately, Nathaniel.
And
Nathaniel, you're with me, buddy.
Most guys.
And Liam. Me and Nathaniel and Liam.
So guys, I think what we need to do is we need to print t-shirts that says, be like Jamie. Like, seriously. Jamie, can I call you out? Like, this girl can organize and communicate calculations like no one on the planet. Oh yeah, WWJD. What would Jamie do? You're good at this. All right, so guys, are we settled on that? Now, guys, read your chart. Read your tabley schmably thing. It is equal do I have this in my slides? I don't know. Let me look. I think I may have put this here. If I didn't, we're just fine, but I don't know if I did. No, you know what I did is I actually did this. So we'll go here. So guys, what was our number 2 what? See that right there?
That's magical.
Right? Okay. Now guys, do this. Go to this table, and this is the way I described it. I said the pH is equal to the ion concentration of the original equilibrium solution, the 0.1 molar acetic acid, the icebox. Is that okay? Okay. So now guys, let's go before equivalence. Now we're going to talk about this region right here. And guys, the question reads like this. Yeah. How did that happen? Sorry, hold on. Oh, this is the one that I wanted. Okay, here we go. Yeah, here we go. So it says calculate the pH. No. Guys, hold on. Sorry. So this is the one we just solved. Oh, there it is. Why did I do that? I don't like that. Luckily, I'm in charge, so I can fix it. I really think all I need to do is this. We know the Ka. Yeah. Okay. So guys, here's where we're at. This solution is titrated now. Oh, I know why I left it. Yeah, guys, the reason that I left it is because we need to know the volume of the initial acetic acid and the molarity. That's why I left it. Okay, so guys, with that said, let's put this in context. So now we've got 45 milliliters of the base dumped into the vinegar. So guys, where does that put us on here? Nora, you have the laser.
I do.
Where does that put us up here?
Right there.
But can you be even more specific? And if you put your elbows on the table, you can like totally be like, yeah, sniper.
Okay.
Yeah. So guys, we're right about there, right? So where should we be? Somewhere around 6?
Yeah.
Let's do it. Okay. So guys, hold on, I'm curious. Yeah, it didn't. I want to redo the way I've done this. But this is where we are now. So given Nora's mad sniper skills, we're thinking we're going to be somewhere around 6, right? So let's do this. But guys, before we do, let's draw a picture. Oops. Let's draw a picture. All right, that'll be my burette. So guys, here we go. So let's think our way through this. So guys, down here, we've got 50 milliliters of 0.1 molar acid. Up here, we've got 45 milliliters of 0.1 molar strong base. You okay on that? So guys, this becomes the question, and I'm going to ask it in a way that should bring back some memories. Guys, what does this strong base do to this acid?
It raids it.
It raids it. It pillages it. And guys, the pillaging looks like every NOH that we put in there, one of those acetic acid molecules, starting to sound familiar, every one of these that goes in, an acetic acid molecule dies. But guys, do all the acetic acid molecules die? Ooh, talk about that together. Do all the acetic acid molecules die? Talk about it.
No.
That was easy. No! Guys, why not? And guys, the reasoning is this. And you're right, same molarity, smaller volume. So we've added less of the raiding hordes. But guys, be careful. Be careful. They're going to do this to you on the AP test because they're evil, right? That demigod that said write better, he's actually an evil demigod because his job is to make you do bad. So here's what he's going to do. He's going to make this 0.2 molar. Right? And now, guys, all of a sudden you can't say we added less of the rating hordes because it's by moles, and that's twice as concentrated. So how do you actually figure it out? Do some dimensional analysis and convert to moles. Right? Okay. All right, but back to where we were. So, guys, going back to the rating hordes analogy, can you see it? Oh, man, guys, and this isn't a buffer, right? But vinegar's down here, and it's chilling, doing its equilibrium thing, giving away a hydrogen. Yes, takes it back. It goes back. It's all equilibrium, right? And then, guys, in comes the sodium hydroxide, and it's shnikes, right? Guys, those sodium hydroxide molecules kill some of these acetic acid molecules. How many? As many as NaOH is what we add. But they don't all die. Some of them actually survive the onslaught. And then what do? They go to equilibrium. So guys, how mathematically do we deal with that idea of an equilibrium that gets its trash kicked and then it comes back to equilibrium? I-race box, let's do it.
We should take this one slower.
Oh yes. Yes. Yes, we will.
Not do the insane.
I know, and let's make it blue so it seems less threatening. Go ahead.
I guess I'll ask after.
Okay, so guys, I-race box, here we go. CH3COOH in equilibrium with then IR, skip a space, A. What did we say our goal is, like 6?
Yeah.
Okay. So, guys, I'm going to ask you to do some legwork for me. So, guys, in the I-race box, we need to know our initial moles or molarity? Moles, because this is butt kicking, right? This ain't equilibrium. So, guys, we need to know how many moles of acetic acid we've got. Can you picture the math? It goes 50 milliliters, 1,000 milliliters is a liter. 1 liter is 0.1 moles. That's pretty. So 50 divided by 1,000 times 0.1, so 0.005. So 0.005 moles. And guys, I'm just going to be a little loose with significant digits. That's not right. It should be 3. That's only 1.
It's fine.
All right, then, guys, none of this, none of this.
I think we should rename acetic acid. Call it GR.
There you go.
Maybe sometime.
Then, guys, we need to figure out how much of the rating horde stuff goes on. So we are adding a base. Remember how we think about this. We put OH up above the yield, the equilibrium arrow. But, guys, OH is going to drive the equilibrium in this direction. So how much of that is going to take place? And, guys, the answer is 45 milliliters, 1,000 milliliters, 1 liter, 0.1 moles. So it's 0.0045 moles. Yo?
Yes.
So guys, we're going to go 0.0045, 0.0045. And then, guys, what about hydrogen ion?
Nope.
Nothing. Now, which one is plus and which one is minus? Do it in your I-race box. This is why the I-race box is so great. So, guys, this one's getting gobbled up. It goes down. This one's getting created. It goes up. So this would be 0.0005 This would be 0.0045, and this is still 0. Then, guys, we need to divide by the adjusted volume, 95. So 0.095 liters. Is that right?
Yeah. 0.09.
Sorry, guys, that got ugly. Am I okay, though? Yeah?
As long as the decimals we treated to zeros.
Yes. Oh, don't even try to read that. It's the same as this. So 0.0005 divided by 0.095. So I get 0.00526. Let's bring, and you guys understand that there really are zeros out. Let's bring our significant digits back. Molarity. And 0.0045 divided by 0.095. So 0.0474 molar and 0. Is that okay?
Or hydrogen ion.
They're kind of left out.
I know, but starts getting good now, right? Minus x, plus x, plus x. So we have 0.00526 minus x and, oops, 0.0474 plus x and x. How we doing? Are you guys all caught up? Little iRace magic. So guys, I'm out of space, so I'm going to go to a clean screen. So we have Ka is equal to and then 1.8 times 10 to the negative, 10 to the negative fifth is equal to, so acetate ion was 0.0474. 0.0474 plus x, wow, times x, and then 0.00526. Wait, 0? Yep. And that's approximately equal to 0.0474x divided by 0.00526. And then x is equal to,
X is equal to 1.8 times 10 to the negative fifth over those two numbers.
1.8.
Do we get rid of the other x at the top?
No.
The 0.0474.
So we got rid of this x and this x. So we have 1.8 times 10 to the negative fifth times 0.00526 divided by 0.0474.
2.0 times 10.
6? Yeah. So 2.00 times 10 to the negative 6 molar. Then guys, I'm going to cut some corners here. pH is equal to the negative log of 2.00 times 10 to the negative 6.
That's 5.7.
So 5.7. So guys, the pH is 5.70.
Hey, almost what we thought it was.
Yeah, and obviously, guys, the graph, right? When we say the graph, we mean, when we say the graph, we mean this, right? So we were looking at like 45 milliliters. We're in the ballpark, right? The answer is actually 5.70. But we see now where that came from, right? Okay. So guys, we still need to solve the last two. And we're going to, but we're going to take a break, yeah.
So I guess what makes this doing this iris box different than doing it for Urban?
Great question. So, guys, Nora's question is, how is this different from when we erase a buffer? And I'm going to turn it to you as a question. So, this isn't a buffer. Why is this not a buffer?
Because the pH does change. And it goes
Correct.
to
But and that's great evidence that it's not a buffer. But physically, what is it about this that doesn't make this a buffer? What's it missing?
You're not adding something else.
What is that thing called?
The parent.
Yeah, not the common ion salt, right? So we didn't buffer this. And because we didn't add the common ion salt, the math is the same, but the idea is we don't have an excess concentration of this. But that said, the math works the same because we're still adding something strong to something weak. Is that okay? Sharp, go ahead.
So it kind of functions as a buffer, like the math kind of functions as a buffer for this way, but if we were trying to go the other way, it wouldn't work at all.
No, exactly. Yeah, exactly.
It would
Right.
just crash and burn.
That's exactly the point, because there is no acetate ion that could fight against a strong acid.
So
Exactly.
this is saying this is like the OH that we're adding to this is from the base.
Correct.
That we're
Yes,
adding.
yes, yes. Yeah, so
But it's not the conjugate, or like the common ion, or whatever.
correct. Yeah, so I don't know what this is going to do. Yeah, so the hydroxide that we're adding is coming from there. Is that okay? Guys, let's do this. I don't want to take a break early. I just want to give you guys a couple minutes to just go, oh.
It wasn't that bad.
Then, I know, but it's been bad for me. I need a nap. No, I'm just kidding. This has been great. But guys, let's do this. Let's take a couple minutes and just sort of decompress. Let's take a break. Then we're going to come back and we're going to solve the one at equivalence. But guys, we got to be sharp on our toes for this. So, with that said, this is what relaxation is going to look like for us. Go back here and look down here. What did we just do to find the pH at equivalence? And I said this. It's equal to the ion concentration of the unreacted particles. That's the subtraction in the I-race box. Then an adjusted equilibrium, that's the CE in the I-race box. And then guys, remember volume changes when we converted from our moles to our molarity. We divided by the 0.095, the sum of the volumes of both of the things that are doing the chemistry. How are we doing? So guys, settle into that, edit that as you will. And as they say in theater, take 5, smoke if you got 'em.
Except for not.
Have you guys ever heard that? Is that
Never heard that saying.
really?
All the kids are doing.
Take 5, smoke if you got. No, never mind. Okay.
No, I've heard. We're too young.
Distractions away. Thinking caps on. Guys, this one's funky. And I know you have no frame of reference, but the way that I teach you to do these, you're going to be thankful. So, guys, and maybe you've picked up on this. Guys, the thing that makes the way that I teach this to you advantageous, and again, you don't even know this, right? When we graded the buffer homework, you're like, yeah, we're good. Shouldn't have been. But you were, because you understand the chemistry, right? Most of the time when they teach this stuff in college, they don't even try to teach you the chemistry because they're university professors and they don't think like 19-year-olds. They think like people with PhDs in chemistry, and to them, all of this is so stupid easy that they've never thought about the possibility that it could be hard, and as a result, they certainly don't know how to explain it to a 19-year-old. Guys, this is funky. but stick with me. And because you understand the chemistry, you're going to get this. So guys, here's the question. What is the pH at equivalence? That's it. What is the pH at equivalence? But guys, in order to talk about this, let's look at where we are on the graph. So this is our titration curve. And you understand that we're talking about equivalence. Now guys, we've already flirted with this idea. We're going to do it mathematically in a minute. But guys, it's important you understand why the pH is not 7. And we threw this up on the board a moment ago. But the idea, guys, is that by definition, the salt that is formed when a strong base and a weak acid react together, that conjugate ion is the child of a weak acid. And therefore it does chemistry with water. You get the idea? Okay. So guys, with that said, we have got to be able to figure out exactly what this is going to look like. So guys, again, we're coming back to this idea of figuring out the pH at equivalence. So I'll let you get caught up, I'll let you get settled, and then we're going to do this. Are you okay right now? You okay? Okay. So guys, what we've got to do, and just so you know, eventually this is going to be an icebox. But guys, we've got to do some thinking before we can get to the icebox. So guys, join me and let's take a look at this. So guys, let's look at the chemistry that's taking place. Oh, wow. Okay, board, I'm going to write on you, and I'm going to need you to pay attention. So guys, all that we're doing is we are representing the chemistry that's going on during this titration. So guys, I'm gonna back you in. I'm gonna lead you in to how to think about this icebox. So guys, when you're ready, I don't want you to miss the thinking. If you understand, you'll be good at. Oh wait, I didn't want those charges there on that, because really, well, I want the one but not the other because we wrote this. Okay. Okay. So guys, thinking then. Let me make sure I can write. Okay, thinking then about the chemistry. Guys, we are at equivalence, right? What's equal at equivalence? Moles of what?
Moles of acid.
Moles of the acid in the base. So, guys, again, and I know pictures kind of dumb until they're helpful. So, guys, we've got this, right? And we've got this. And we've got this. And this had the vinegar in it. And this had the NaOH in it. And, guys, when we reach equivalence, how much vinegar is left inside here? None. And, guys, when we reach equivalence, how much NaOH is still hanging around? None. Right? Guys, when we reach equivalence, we have added equal moles of this, and we have added equal moles of this. And guys, there ain't no equilibrium going on between those two. Sodium hydroxide is a strong base. The damage is done. This is quantitative. And so guys, when we reach equivalence, when we reach equivalence, we've added the same number of moles of this as we have moles of this. And so guys, how much of each one of these do we have left? None. Get rid of them. Guys, that's gone. Sharp, I see you, but let me run with this thought for a minute. Guys, pause. Does that make sense? At equivalence, all of the acid has been consumed by the base. We haven't added any additional base, right? We're not beyond equivalence. So guys, we've added just enough base to gobble up all the acid. So in the solution, we're not going to have any unreacted acid, and we're not going to have any unreacted base. Exactly enough. Wait just a second. We'll go that way, Charlotte.
Did we mean to have hydrogen ion on the end of this?
Oh, water.
I looked at that and I went,
No, I'm like, wait, thank you, no, thank you. I was like, shoot, something's wrong. Thank you, water. My bad. Is that also, Nora, what you were thinking?
No, I was gonna
James,
say,
sorry.
I was gonna ask, is this just, like, in this situation, we can only do that if the, moles are the same?
And that's
And like
equivalent.
the molarity is the same?
No. So let's just make up some numbers. So say, for example, that this was a 1 molar solution and this was a 2 molar solution, and say that we had 50 if we had 50 milliliters of this.
Cause it's like we're just snapshotting it, right?
Correct. But let's talk about it. So if the acetic acid was 1 molar and we started with 50 milliliters, how many milliliters of 2 molar would it take to neutralize it? 25, half as much. So we can get to equivalence any way we get there, but the volumes won't necessarily be the same if the molarities aren't the same. Is that okay? James, you had a thought.
Oh, I think
Okay, so guys, are we good there? Okay, so guys, what that means is this. In our flask, down here, when we reach equivalence, this is what's in there. Sodium acetate and water. Thank you for correcting me. Sodium acetate and water. McKenna would say what about sodium? Trash. This ain't no trash, right? Because that's the thing that we icebox.
We icebox that water.
That's the thing that we icebox. We icebox the acetate ion messing around with the water. Now, guys, understand, it's not just the water that gets produced by the neutralization. It's also the water that these things are already dissolved in, right? And so, guys, what we are going to do is we are now going to set up. Wait a second.
Plus water.
Yeah, do we need it?
Well, if not,
Well, I mean, it's not.
Oh, yes, we have to have it. It's a reactant. No, yeah,
But
wow.
It's not going to do anything in the icebox.
Well, but
Yeah,
It's
but-
important to have it.
yeah, but it kind of balances the equation. So what would make most sense? It doesn't really matter. There we go. Okay. So now, guys, we need a little ice box.
Maybe icebox.
And as some have said, this doesn't change. But now, guys, the tricky bit. And I'm gonna ask the question, and then I'm gonna go back a screen to show you how to get there. So, guys, before this does chemistry, these are 0, right? It's an icebox. But we need to know what about the acetic acid. What satisfies this? The molarity, right? Because, guys, we need to know the molarity of the acetate ion in order to figure out its equilibrium concentrations. Where on earth, how on earth, are we going to come up with the molarity of this? So, guys, you ready? This is the reasoning. Speaking in moles, how much of this do we have? Not a number, a concept.
As much as
the vinegar.
As much as the vinegar or this, right? Because those moles are the same. We're at equivalence. And so the moles of this and the moles of this are the same, and they're all gone. And where did they go? They turned into this. So, guys, the number of moles of this that we've got are the number of moles of either one of these that we started with. Does that make sense? So then, guys, we do actually need to know the volume. It's 50 milliliters, right? So really quick, 50 milliliters. 1,000 milliliters is 1 liter, 1 liter, 0.1 moles. So is it 0.005? Right? So guys, we started with 0.005 moles of either one of these. So what that means is we now have 0.005 moles of this. But why don't that go in the ice box? We need the molarity. So now we need to know the volume. And guys, how much is this floating around in? Yeah, because we've got 50 milliliters of this. Because the molarities are the same, the volumes are the same. So that would be 0.100 liters. And that would be 0.05 molar. So guys, yippee skipping over here, this would be 0.05 molar. But guys, I don't want to go past that too quickly. That's the thing that makes this tricky, y'all. The way to approach this is at equivalence, you write down the chemistry that's going on in the neutralization. Then you figure out which one of the ions in the salt is going to do chemistry with water. Then at that point, you set up an ice box with that ion doing chemistry with water. Then you've got to go back and figure out the molarity of that ion. But guys, the molarity of this ion is the same as the number of moles of either one of your reactants, because it's an equivalence. Either one of these reactants converted to moles because you're adding the two solutions together. All right? Guys, seriously, the fact that, one, I was able to even think and talk my way through that, and two, you weren't totally bam schmoozle confused. Guys, you're learning chemistry in a way that you probably won't until deeper into your college career. Because guys, for the most part, the way they teach this in freshman chem is they just throw numbers on the board and they're like, guys, you understand the chemistry. So what questions do you have about that process? Write out the complete equation of the neutralization. Figure out which ion is doing chemistry with water. Icebox that ion against water. And then figure out the molarity of that ion by figuring out the moles of either one of the reactants, because we're at equivalence and they're the same. And then divide by the adjusted volume because we've got an additive amount of liquid. Because that's a lot of stuff. Do you need to unpack any of it? You okay? That's pretty cool. I love you guys keep saying that's easy. You realize it's easy because I'm good at this, right? Sorry, I had to say it. But it's actually, I can't wait for you guys to get to college.
Apple fritters for what?
For me, right? For me.
We'll bring you the apple fritters.
You should, because so
We'll pay
that
for this.
day
One for every
when
dozen.
you propose to that girl that you met in your freshman chem study group,
Fair.
You'll be invited.
invited, I should be the best man. All right. So guys, now let's do icebox stuff, shall we? All right, so now guys, we've got to be careful. This is a KB question, right? Yeah, it gets worse. KB is all right, guys, where are we going to get KB for acetate ion?
Google.
Ooh,
You got to know
the
this.
AP equation sheet.
No. So guys, here's what we do know. The Ka of acetic acid is 1.8 times 10 to the negative fifth. How do we figure out the Kb for acetate ion?
K equals
Ka
Oh, yeah.
times KB is equal to KW, which is 1 times 10 to the negative 14th. So we go, plugging in Ka is 1.8 times 10 to the negative 5th. So we go 1 times 10 to the negative 14th. Divide that by 1.8 times 10 to the negative 5th. And guys, the KB for this is 5.56 times 10 to the negative 10 is equal to x squared divided by 0.05 minus x, which is approximately equal to x squared divided by 0.05. So we go this times 0.05, take the square root, and I get the molarity as 5.27 times 10 to the negative 6. Then guys, I'm going to get sloppy on you. POH is equal to the negative log of 5.27 times 10 to the negative 6 is equal to 5.28. Then pH plus POH is equal to 14. And guys, I'm out of space. So 5.14 minus 5.28, 8.72. So check me, but that's 8.72.
Agrees, I think.
Just give this to your drunken students.
Yeah, that wouldn't even be fun because they wouldn't actually even be able to experience the trauma because they wouldn't even know where to begin, right? This only hurts if you think you know what you're doing, right? Yeah. Yeah, it's like, hey, go climb that mountain. If it's Timpanogos, you think you might be able to do it and you sort of give it a try. If it's like Everest, you go, no. And then it doesn't hurt, right? Yeah, right. So, guys, yeah? Okay, now I'm curious. 8.27. Boom. What is happening? Boom. Boom. Boomy boom. Boom, 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 boom. Yeah,
Yay.
that works. Close enough for government work. Yeah? Not bad. Guys, thoughts on that? Okay, now guys, this. Now we're going to go after equivalence. What do you notice about the two lines? They're the same. They're superimposed. I'm fearing I'm making this transition too fast. Guys, do we need to camp more on the at equivalence calculations? Okay, now let's do after equivalence. So guys, after equivalence, remember what's going on. So after equivalence, guys, after equivalence, this chemistry is all done. So at equivalence, guys, at equivalence, this is gone, we're left with this. And guys, we demonstrated that the pH of that was 8 point whatever. 8, I don't even have it. But then guys, what if we keep adding base? What if we keep dumping base into this? Well guys, if we keep dumping base into it, this is basically water, right? It's water that's been mucked up a little bit by some acetate ion. Guys, it's basically water. And as you dump more base into the water, guys, the pH just keeps going up, just as if it was a strong titration. So guys, the math is exactly the same after equivalence. How many moles of base did you add? How many moles of acetic acid did you start with? Subtract. That leaves you with the amount of sodium hydroxide that's in excess. Turn it into a molarity and take the negative log. Yo. Okay. So guys, now come back to this and we're done. So that wackadoo crazy thing that I wrote up on the board where we were figuring out the pH and equivalence, this is how I summarized it. It's not 7 due to the hydrolysis, the breaking apart of water by the resulting salt ions. It can be calculated doing a Ka or Kb calculation on the conjugate ion from the salt. Because that's missing so many little details, right? So maybe you want to write down the details, like the amount of conjugate ion is the same as the amount of the initial either one of the participants. Then you convert to molarity by dividing by the adjusted volume. I don't know what you want to add. And then guys, you'll notice the after equivalence is the same top to bottom. We're done. So, can I ask this? Guys, with this down at the equilibrium part, this is all the concepts, right? Would it have been helpful to put also the steps?
Yeah. Steps are always nice.
Steps are nice. Because at the end of the day, who cares if you understand this as long as you can do the math? Again, college.
So, for this one, last time we did strong, like strong, and today was that strong weak.
Correct.
And so, are we doing weak, weak?
No,
We-
because those are the competing equilibria.
Okay.
Yeah.
When with this where it says equilibrium, AB,
Where am I looking? Oh yeah, so that's the weak guy, right?
can I just write?
Yeah, sure. I mean, because realize what we're saying is, so what reaches equilibrium? That's something that's weak, right? And everything that we looked at was weak acid, strong base. We could also do this for weak base, strong acid.
It would just be backwards.
Now it would all be backwards. Alright, notice you still have my laser.
Yeah, you're welcome to take it. Would
Did
you
I guys
like
ever
to-
tell you about my dream where I wish that I could actually take that laser and increase the power so that it hurts?
You should definitely do that.
That would totally revolutionize classroom behavior management.
Bring back corporal punishment.
Yeah, right?
But with
no one
nerves.
would know.
Laser.
But with laser beams.
Right, just go.
I mean, I feel like
It
if
was like
it
like
was strong enough to
concentrated
hurt, that it would probably make a mark.
I don't know, maybe. It would be like a long distance cattle
What
prod.
you need to do is you need to make it like in like ultraviolet or whatever.
I need to give you a sunburn. Oh, it'd be like a freckle. Wasn't me, you have freckles.
Exactly. I can't help
Okay, I gotta stop recording.